Hello and welcome to this new video where we discuss mathematics and physics on the board. In this video, we are actually going to apply something we've seen in a previous video, which is the Legendre transformation. If you remember, the Legendre transformation is a situation whereby you've got a convex function, or at least that's what we've seen so far. There's a convex function, and then you basically say that you can characterize this function by providing a pair of numbers, either the x that is in the domain of the function, and then basically the image of that function, so the f of x, so x and f of x, or you can provide equivalently a set of values for the slope and intersect of the tangent to the graph of that particular function. And as it turns out, it's going to be actually in terms of mapping, it's a map from the reals onto the reals as well. And this is going to be a dual representation of the original function you wanted to talk about. Okay, so that's what we've seen. And basically here, what we are going to see is that we can apply that strategy in Lagrangian mechanics to go to Hamiltonian mechanics. Okay, so here I'm assuming that people have had some exposure to Lagrangian mechanics. If you haven't had any such exposure and you would like me to somehow expand a bit on what are the principles of Lagrangian mechanics, how it works, and so on, by all means, do let me know in the comment section, and then I will provide some more kind of basic material on the subject. But the bottom line of Lagrangian mechanics is that you have something called an action, and here I'm basically in 1D, so I'm imagining some like an object that is subject to some force or whatever, only in one dimension. Okay, and so x here is representing the position of like a point object in 1D. Okay, and that depends on time. And then basically we call the action S this quantity here. So that's the integral of a function, and this function is a function only of the coordinate itself and its time derivative x dot. So basically its velocity. And it can also be also dependent on time in some kind of explicit fashion, but basically that's it. So you've got this function here, and then you integrate that over time, and you get what is called the action. Traditionally, the goal of Lagrangian mechanics is to say that if you try to find the function x of t that basically makes S minimum, that's so-called the minimum action principle, then, or least action principle, then you're going to, then the equations satisfied by this particular extremum solution, so x of t, are going to be the equations of motion you would have from Newtonian mechanics. Okay, so it's a sort of minimization principle that is very much akin to Fermat's principle in optics, whereby you say that you want light to travel along path of the least time. To go from one place to another. Okay, so here it's very similar, except that the quantity to maximize or to minimize here is what we call the action. Okay, now that's kind of just a bit of background. Again, I can go much deeper into this if you want to. Just let me know in the comment section. So the Lagrangian is a typical function that usually people would try to guess or reverse engineer based on their knowledge of Newtonian mechanics, or to justify based on symmetry arguments. And the reason why Lagrangian mechanics has become so popular is because of how symmetry can be used to infer the general, the most general expression, say most general truncated expression of Lagrangians for particle physics, for example, given a certain set of symmetries. And so here it doesn't, that also works that way. This is something I can go into if you want as well. There is a proof that is provided in Landau for this particular expression here. But again, this is something I can go over if you need to. But in any case, the typical expression of the Lagrangian is the kinetic energy, so half of mv squared. Remember, x dot is simply the velocity, and then minus v of x, which is the potential energy of x. So please note the minus here. There is an actual minus v of x. Okay, so it's not the same as the total energy of the system. Okay, so what you can do then is say, okay, let's try to plot, so to graph L of x dot t if I fix t at some kind of value. Okay, and so here that's what I'm plotting. So I'm fixing t. Sorry, if I fix x at some value. So here I'm fixing x, and what you can see is that essentially we've got a parabola, and the actual equation is half of mx dot squared, and I'm plotting that as a function of x dot. Okay. Now what the v of x is going to do, so I fix x, and the v of x is simply going to shift this curve up and down, but basically that's it. So what we notice is that that's what I'm writing on that side, is that at fixed x, we've got that L of x dot is convex. And what we've seen is that if we have a convex function, then we can use the Legendre duality. So the thing is that we can use the Legendre duality. And what is this duality? The duality is basically that we've got either we represent, so the physics, if you will, the physics of the system captured by the Lagrangian function can be expressed as having a pair x dot L of x dot. And again, imagine that x is being fixed, so physics at fixed x, just so that we are clear. So I can provide a pair x dot L x dot, okay? But I can provide here basically what I call P, and which is a slope of the function L with respect to x dot, okay? And so P here is actually dl dx dot, okay? Because that's you want to have the slope of the function L with respect to x dot, exactly like what we did in the Legendre transformation video. And then you want to return what I'm going to call for now L star of x and p. Okay? So that's what you want. And what we had is that we have that L star of x p is equal, by definition of the Legendre transformation, is equal to L of x dot, and then minus p x dot. Okay, and here I need to remember or to remind that this is when x dot is evaluated as being dl dx dot, but then to the minus 1, so that's a function basically, and then evaluated at p. Okay, so I want the inverse function of this, so whatever that function is going to be, I want the inverse of that to basically get x dot as a function of p instead of p as a function of x dot. That's basically what I'm saying. And so you can also just write that as x dot of p. Okay, that's the only thing we want in the end. Okay, so here this is something we can do with what we have. So we have that L is equal to half mx dot squared minus v of x. So what do we have therefore? dl dx dot is going to be equal to mx dot. And if I say that this is equal to P, then it follows that x dot is equal to P over M. Okay? So once we're there, we basically are almost done, because then I say, well, L star is equal to, so L star is going to be equal to L, so that's half, M x dot squared is like P squared over M squared, all right? And then we still have, so this is minus Vx, that's still there. And then I need to subtract here. So I've got minus P times x dot, so that's P squared over M. And this is equal to minus P squared over 2M minus V of x. Now, this is a Legendre transformation of the actual function of the Lagrangian relative to the x dot variable, to the velocity. So we essentially replace the velocity by the slope of the Lagrangian function relative to x dot. Okay. Now, so we've got basically a dual way of representing things. Now, what people do then is basically remarking, that's something we've done before in the previous video, that this is actually a concave function. Okay, and what people would like is actually to have a function that is basically convex. So the Lagrangian was convex. That's basically, it was curved like up like this. So we want the dual function to be convex here by convention. Okay, it's not like this is an obligation, but by convention. And this convex version of the Legendre transformation is what we call the Hamiltonian function. And so we define Hamiltonian as being the following. It's h of xp is equal to minus simply the Legendre transformation of x and then p. Okay, that's basically what we do. And if we do that, what we notice is that this is equal to p squared over 2m, and then plus v of x. And basically, this is interpretable as being the total energy of the system. Okay, that's not necessarily following from that, but that's something that we know. So this term here is going to correspond to the actual kinetic energy. You can kind of verify that just by substituting again P as being x dot times m, and then you're going to see it's actually the kinetic energy. P here is going to correspond to the momentum. So we recognize plenty of things that basically come in here. But basically that's how that works and how you go from one to the other. Now, at that point, I have not yet talked about the equations of motion, but that's a different topic altogether, okay? So for now, I'm going to stop here. For once, it's not like a huge it's not a big video. It's a short video to show you how to apply the notion of Legendre transformation when we want to go from Lagrangian onto Hamiltonian, and essentially with maybe now a slightly better understanding, or maybe equivalent understanding with one you had before, maybe, in terms of what we are doing when we do that. Essentially, again, we substitute a characterization in terms of a specific coordinate x dot with basically a characterization in terms of the slope of that particular function here. So the kinetic energy as a function of x dot. That's basically what we do. And so once we provide that particular slope, then we just need to provide the intersect of that slope, and that's actually L star. Okay? So that's kind of the magic of it. Now, like, the beauty of it is that it turns out that minus the Lagrange transformation is actually the total energy of the system. So it's quite beautiful, and there is a lot of interesting, deep, kind of fundamental results behind this duality between Lagrangian and Hamiltonian. But no matter, in any case, if you've got any questions or comments on this, by all means, do let me know in the comment section. And otherwise, see you in the next video.